Lecture 56, conservation of energy and momentum in special relativity. We're going to start with a correction from lecture 55. There was a typo. Forgot to put in a square factor, but the correct formula should have been E squared equals the quantity gamma PC squared plus the quantity MC squared squared, right? Where this is such that, well, if the momentum is zero, such that we're just considering the rest energy of something, so it's not moving relative to us, then the momentum would be zero. And so we get E squared equals the quantity MC squared squared. We take the square root of that, we get E equals MC squared, the rest energy. Okay? Note that E squared is gamma MC squared squared. Now, there's a lot of squares in there. So we, of course, we're going to let C be 1 as usual, right? Making this go away, and this go away, and this go away. Okay? And so in today's lecture, we're going to talk about conservation of energy and momentum for an inelastic collision, which in classical, or in Newtonian physics anyways, energy wouldn't be conserved and momentum would be. You might remember that when we worked these examples of inelastic and elastic collision out. Elastic collisions, we had conservation of energy and, of course, conservation of momentum. But in inelastic collisions, we had conservation of momentum, but not conservation of energy. The logic is that the noise you hear when the two clay balls slam into each other, they deform. Right, so all the energy that was there is going into the internal energy of the clay and also into making sound waves and stuff like that. Well, the relativistic version of this accounts for all of that, and so we get conservation of energy and momentum always. And let me show you how we do it. But you have to do it a little bit differently. So instead of using P equals mv for momentum, we're going to use this term gamma P, where this factor of gamma has the velocity of the particle in it. And we'll see that in more detail soon. And so that's what we'll use for momentum. So we'll have to consider gamma P instead of just P. For energy, we're going to use gamma M. So gamma M for energy. And so let me just show you how that goes. I'll also point out that you can solve conservation of energy and momentum in the train frame using this relativistic formulation, and I'm going to leave that as a homework assignment. I think that if we do it in the platform frame, you'll see how this is done. It'll actually be easier in the train frame than in the platform frame because of the velocity, the addition of velocities aspect. So here's our system. We have two clay balls barreling towards each other on this train. The mass of both clay balls is the same. The velocity, they're equal and opposite in sign, okay? And the magnitude of their velocities are equal to the magnitude of the train's velocity. This is just to make the math, the algebra easy, okay? After they collide, they stick together, and so they're now, in the train's frame, they're not moving, they're at rest. And they have a new mass, big M. And so we're going to find out what big M is in a minute. In the Newtonian version of this, or the Galilean version of this, the mass, big M, would just be 2 times little m, right? Because the two masses have come together, okay? And so this is an illustration of how in relativity mass is created. And we'll talk more about this later. I originally was planning on doing particles, muons and electrons and protons and quarks and stuff like that. Next, I changed my mind about that. We'll do that later. But there we will see that the mass of, say, the proton mostly comes from something similar to this. It's a little bit like our spring that we weighed on the scale, and then we compressed it and clamped it down, so it was compressed, and now it weighs a little bit more. It turns out there's a very significant contribution to the mass of the proton that comes from this kind of clamping, where it has to do with the potential energy of the quarks inside it. But we'll get to that. So what do we need to write down first? I think we need to summarize what the velocities before and after are going to be in the platform frame. And so we can write that v1 in the platform frame, right? If it was just Galilean relativity, we'd take the velocity in the train frame and add it to the speed of the train, right? So we can do that here. Remember that the speed of this particle 1 is u, the same as the speed of the train. So we can have u plus u, which of course is just 2u, right? So write 2u here. And that would be true for Galilean relativity, but in special relativity, you'll recall that we had to divide that by 1 plus, and it would be the speed of the train, u, times the speed of the object, which is v1, but since they both have magnitude u, this will be u squared. Okay?
All right.
v2 in the platform frame, right, as measured by the observer on the platform. I pointed at the wrong picture. v2, right, is going to be equal to u minus u. Actually, it's minus u plus u, because minus u is the speed of the particle, plus u is the speed of the train. Then we would divide by 1 plus u squared again. It will actually be 1 minus u squared. But since u minus u is 0, this is just 0. Okay? V sub f, that's the final velocity of the clump, the two masses clumped together. Right? That's 0 in the train frame, but in the platform frame, it's going to be that velocity 0 plus the train, which is u, okay, divided by 1 plus u times 0 is just divided by 1. So the velocity in the platform frame is just u. You can think about that. Since it's not moving with respect to the train, it will have the velocity, the same velocity that you perceive the train having, right? Because it's moving, it's stationary with respect to the train, right? So it too is moving at the train speed. Okay, so now on to conservation of energy first, okay, in the platform frame. Now, how we would do this classically is we would say that T sub B is equal to 1/2 mass times the velocity squared, or V1 squared, right? But with relativity, this is the expression we need to use right here, gamma m. And specifically it's gamma 1 and m1, but m1 is just equal to little m, so we'll leave this as little m. Plus gamma 2, little m, right? So that's the second particle. We add those together, you see? Now, what is gamma 1 and what is gamma 2? So let's calculate what gamma 1 is real quick, though it's not that easy to calculate. There's a bit of algebra here. Gamma 1 is equal to 1 over the square root of 1 minus v1 squared. Okay? And you can see this is going to be messy because this is v1 squared, right? I shouldn't have outlined that, but that is v1. And so we have to square that quantity, right? That's going to look like a mess. It's going to be like 1 over 1 minus 4 u squared over the quantity 1 plus u squared squared, right? Starting to look kind of messy, right? So we can work on this a little bit. Right, let's just work on the stuff under the radical sign for a minute. Right? We get, obviously we want to give it a common denominator, so this would become 1 plus u squared squared minus 4u squared, all divided by 1 plus u squared squared, right? We square that out. That's going to give me u to the 4th from this u squared term, plus 4u squared plus 1 minus 4u squared, all divided by 1 plus u squared squared. You can see that the 4u squareds will cancel, and we're left with u to the 4th plus 1. Oh, hang on, I made an algebra mistake here. Where did I get? Yeah, whoops. That's minus 4u squared. Sorry about that. It's not plus 4u squared, it's plus 2u squared. 2u squared. Right?
Yeah.
Okay, good. That looks better. And that, of course, now we can subtract minus 4u squared plus 2u squared. That's going to be minus 2u squared. That gives me u to the 4th minus 2u squared plus 1, all divided by 1 plus u squared squared. Now we have to factor this, right? And so if we do a substitution and we call, v equal to u squared, then we can think of this as a quadratic equation. U squared minus 1 quantity squared, right, over 1 plus u squared squared. Yeah, I can factor out a minus 1 out of this, right, with impunity. Because if I factor out a minus 1 and pull it outside the square, if I square minus 1, it's just 1, right? So this can be written as 1 minus u squared, right? 1 minus u squared. Okay, it's looking a little better. And, of course, I can pull this square out, right, and put the square on the whole thing. And why would I want to do that? Well, because remember, this sits underneath the square root sign, right? So the stuff in the radical, I can now replace with 1 over the square root of all of this stuff, 1 minus u squared over 1 plus u squared squared. Right, and the square root of a square, of course, is just the thing that we're taking the square root of, so this is going to give me 1 over 1 plus, or excuse me, 1 minus u squared over 1 plus u squared, which I can rewrite as 1 plus u squared over 1 minus u squared. So, algebraically it's a little messy. I think that you can do it, though, if you were to try. That gives us gamma 1. Fortunately, gamma 2 is going to be quite easy. Remember what that is? I think I can remember that. Now we have gamma 1. Gamma 1 is equal to 1 plus u squared over 1 minus u squared. Gamma 2, right, is just going to be equal to 1 over the square root of 1 minus v2 squared. But v2 squared is 0, so this is just equal to 1, right?
Yes.
Gamma 2 equals 1. So now we can insert these values in here. So the kinetic energy before is equal to gamma 1, which is this 1 plus u squared over 1 minus u squared, times m, plus 1 times m. But I can think of this as m times this plus 1, right? Let's factor out the m from both of them because they're the same, yes?
Yes.
And so now I have this quantity, which I can then do something similar to what we did before. I can rewrite this as 1 minus u squared over 1 minus u squared, so they have a common denominator, right? We have 1 plus 1, and we have u squared minus u squared, so you can see that the u squareds disappear, right? And what am I left with? Just left with 1 plus 1, which is 2, which I can pull out and put it here. 2m. T after. Well, T after is going to be equal to, well, it's gamma of this system, v sub f prime, but that's really just a gamma that just has u in it, right? So I guess we'll call it gamma sub f, which corresponds to this guy here, right? This velocity, times big M. Yeah, okay? You see that? Just using this formula, gamma M. Gamma, it's different than what we're used to dealing with it because it's not just the relative velocity that's in there, it's the velocity of the particle that you're thinking about. When you work this problem out in the train frame, you'll have to do that too. Okay?
Okay.
You have to think, okay, well, this is gamma 1, M1, but M1 is just M, so you still use gamma 1 in this, okay?
All right.
You just won't have to use these velocities, you'll use the easier velocities that you have here in the train frame. So gamma sub f, right, what is that? Gamma sub f, well, that's just going to be 1 over the square root of 1 minus u squared, because v sub f is just u, right?
Yeah.
So that's 1 over, all right, like this, 1 minus u squared to the 1/2, okay? And so gamma f is 1 over 1 minus u squared to the 1/2 times big M. So I'll put the big M up here. Now if we set these two equal to each other, right, what are we going to get? I'm going to write it right up here, if you don't mind. We'll get, setting t before equals t after, I'm going to get this quantity here, which I'm going to change up just a little bit. Put the 2m in the numerator, so it's a little neater looking. 2m will be equal to t after, which is big M, divided by 1 minus u squared to the 1/2. Okay?
All right.
And so, in order for this to be true, we have big M. We're about to discover what big M is, okay? And so all we have to do is multiply both sides by this gamma sub f term here. So we'll get big M is equal to, what was it, 2 little m, right? That's what we would have gotten classically, times 1 over 1 minus u squared times 1 minus u squared to the 1/2. And I don't know if you can see that or not, but this is actually a very convenient reduction that we have here. Let me show you how you can get it. If I now multiply this by 1, but I write 1 as 1 minus u squared to the 1/2 divided by 1 minus u squared to the 1/2. You see what's going to happen here? This times this, right, will just become 1 minus u squared, right?
Yes.
That will cancel the 1 minus u squared here, you see?
I see.
And we'll be left with 1 over 1 minus u squared square root, okay? So this is just gamma. Where now this gamma is just the relative velocity of the train, okay? The one we're used to using. This term here, okay? So this tells us that the mass is equal to 2m times gamma. So let me put that result down here. Big M is equal to 2m times gamma. And since gamma is always greater than or equal to 1, this tells us that the mass of the two particles when they're combined is larger than the individual masses of when they were separate. Okay? And that's something we're going to see, especially in nuclear physics. Okay?
Okay.
That this kind of thing happens, right? Where the sum of the parts is greater than the parts taken individually. You see what I'm saying?
Yeah.
Right? So it's a little counterintuitive because we don't have a lot of experience with things that work that way, but in relativity, it does happen. Okay?
Okay.
And so this is what we were talking about before when we talked about, like cocking the spring, clamping down the spring. We put potential energy in the spring, and now it actually gravitates differently. It has a greater mass. It's teeny tiny, right? When we're talking about things like springs and winding up clocks and heating up a cup of coffee, the mass of the cup of coffee is larger as a result of it being heated, but it's not measurable. Okay.
Okay.
But when you get into nuclear physics, right, the amount of energy is tremendous. Okay, and the atomic bomb is just one example of that. So. Okay, now we have this term for the mass, big M, okay? And I wanted to do conservation of energy first because now we can do the conservation of momentum, and we'll need this big M in order to show that momentum is conserved. And so for momentum, instead of using just P, mass times velocity, we use gamma P, okay?
Okay.
And so it's just like normal, right? We're going to do a P before, and that will be equal to this mass times V1 prime, V1, and so it'll be M, but we need a gamma. I'm sorry, I left out the gamma. And in particular, we need gamma sub 1, right, where the velocity in that gamma is the velocity of this first particle, okay? So we're going to use this gamma sub 1 times M, and then times V1, which is this term here, 2u over 1 plus u squared. And we'll add that to this. And you can see it's going to be subtracted because of it's oppositely directed, its velocity. So that's minus gamma 2, which is just 1, as you know, times little m, times v2. But v2 is 0. Oh, well, that's nice. So that just goes away. Right? So we can ignore that part of it. And so we have p before is gamma 1, m, 2u over 1 plus u squared. What about p after? Well, P after is going to be equal to gamma sub F, we called it, right? It's this kind of gamma associated with these two clumps moving together, times big M, which we have a number for now, times VF, which is just U, so times U. And we can plug in for mass here, and so this will be equal to gamma times 2m gamma, that makes that, make that squared, times u. Okay? And so up here we need to go ahead and substitute in for gamma 1, which was 1 plus u squared over 1 minus u squared, times 2u over 1 plus u squared. And I need a mass in there, times mass. And that's nice because these 1 plus u squareds cancel, right? And so I'm left with 2mu over 1 minus u squared, which I can rewrite if I want to as gamma squared times 2mu. Because 1 over 1 minus u squared is just this squared, right?
Yeah.
If I square this, gamma, then I get 1 over 1 minus u squared. Yeah? So we get a square root, we square it, we get a square root. So we have that. So now we need to say, okay, well, is p before equal to p after? Well, if it is, then we would have that gamma squared times 2mu was equal to, p after is gamma squared times 2m times u. And they are exactly the same. So we see that that momentum is conserved. Okay?
Okay.
Is it a pain in the butt? Yes, it is. And this is a really easy problem. Okay? Imagine if the numbers were not as friendly. Okay? Or if you had more than just these two particles headed for each other this way, it would be a real nightmare. Now, fortunately, when you really have to deal with problems like this, you would use a slightly different approach that does make it a little bit easier, but, well, it actually, when you put real stuff in, it never gets easy. Relativity is just that way. Both special relativity and general relativity, when you try to actually solve real problems, it's just a mess. And there's not much you can do about it. Just work through it. Maybe get Mathematica to do it for you. Mathematica is an algebraic equation solver kind of thing, and so that can make it doable. So I think that's all I want to say about that. So we got that we replaced, let me summarize here. So with relativity, we want to replace 1/2 mass times velocity squared with gamma m, okay? Where this gamma refers to the velocity of this particle here, right? So this would be, let me just write it like this. This is replaced with m over the square root of 1 minus v squared. Okay?
Okay.
You can, as an exercise, you can do the same binomial theorem approximation that we used the other day, and you can see that if v is small, this would be a good homework assignment, that this reduces to this, okay?
Okay.
Kind of. There's going to be a constant term that you'll have to deal with there, but that's not important because we're only ever really interested in changes in kinetic energy. So yeah, so this is special relativity, right? And this is, I'll just call it Newton. Also, m times v, that's momentum in the Newtonian system, right, is replaced with gamma m times v, or if you want to, we can write that as mv over the square root of 1 minus v squared. Okay? So these are the two big replacements that you get. Both of these terms, the gamma m, the gamma mv and the gamma m, appeared so this is the expression that we came up with in the last lesson, where we kind of pseudo-derived this famous E equals mc squared business, right? E is this term that's residing here. And so here's the gamma m that we're using for energy. Here's the gamma p we're using for momentum. And so that's the replacement that you do, okay?
Okay.
So that's what you have to do in order to make energy and momentum conserved. You can show that it's Lorentz invariant, but we know that it is, because this quantity over here was our invariant, okay? The total energy and the kinetic energy by themselves are not conserved, right? But it's the difference in the two that is, okay?
Okay.
All right, I think that's it for relativity for a while. We will use it again when we talk about subatomic particles. Maybe a little bit. We're going to talk about general relativity, but obviously we can't do a lot of it because it involves some pretty serious mathematics. But we'll try to get the concepts across. And I don't know that we'll need relativity there specifically. Actually, there's one instance where we will. I think we'll talk about black holes because they're kind of cool and everybody likes to talk about black holes. And so we'll use some concepts from our space-time diagrams that we talked about in relativity to talk about black holes. Yeah. Okay, so that's it for now.